So now we're going to have a study on the seismic response analysis of lifting ropes in the development of digital twin technology to reduce earthquake disasters in residential buildings. And Dr. Minagawa is an associate professor of the Satami Institute of Technology and is chair of the panel of the elevator safety and reassurance held in the Japan Society of Mechanical Engineering. Thank you very much.
Thank you very much for kind introduction. I'm Keisuke Minagawa from Japan. I still have jet lag. And unfortunately, it's about 10 p.m. in Japan. So I will do my best not to fall asleep during my presentation. Today, I'd like to talk about seismic response analysis for the digital twin. So what you see here is the agenda of my presentation. So first, I will talk about the introduction, the motivation or background of my presentation. Then I will talk you what the earthquake disaster digital twin is. Then I will show you analytical method and the seismic response analysis result of wire ropes. And then finally, I will make a brief summary of my presentation. So let's start with the introduction. According to the Japanese government survey, a proportion of apartment to total housing in Japan is about 44%. Particularly in Tokyo, there are 250,000 apartment buildings with 50 stories or more. So for this kind of building, lift system is very critical, important, very essential facilities. So stable operation of lifts is very important during or after earthquake. On the other hand, according to the Tokyo metropolitan government, a very strong earthquake directly under the capital, directly under Tokyo, would shut down up to 20,000 or more lifts only in Tokyo. Left picture shows typical damage of lifts by earthquake. The original position of the governor rope was here, but due to vibration by seismic wave, finally the governor rope is caught here. So even if the structure doesn't have particular severe damage, this kind of damage of lift system induced closure or stop of lift system, and this kind of closure of lift has a significant impact on daily lives of apartment residents due to increasing building heights and an aging society in Japan. Meanwhile, in information technology field, the digital twin is recently proposed and applied widely, especially for the rare accidents such as earthquakes. So in this presentation, I'd like to propose an earthquake disaster digital twin for residential building. And we have already done some seismic response analysis for the earthquake disaster digital twin. So I will report in this presentation. So anyway, what is the earthquake disaster digital twin? The digital twin technology is a technology that builds an accurate model in a virtual space that is identical to a structure such as factory or transportation system to simulate what happened in the accident in the factory or transportation system. It's almost like a twin. And the earthquake disaster digital twin we proposed is a digital twin that can predict and estimate damage to apartment residential building during earthquakes. So we have to build identical analytical model like this. So we construct a very large research project team, and now we are trying to construct earthquake disaster digital twin. Our earthquake disaster digital twin includes earthquake ground motion, and also building response and damage, and furniture damage of furniture facilities, and also, of course, lift and lifelines such as gas or electricity or water. And also, we consider behavior of residents. The behavior of an entire building is simulated by using design information of the building or lift or something like that, and the dynamic characteristics obtained from or monitoring or sensing. So the result obtained by the digital twin can be useful for disaster prevention or creating improving evacuation plan and the seismic reinforcement. So I am in charge of this lift part. As you know, the most typical damage of lift system by earthquake is rope vibration. So firstly, I construct analytical method of rope vibration analysis. This equation is for the analysis of rope vibration. And this is the equation of motion for lift ropes based on typical wave motion. But we can consider the variation of tension due to the car vibration, vertical vibration of the car due to the lateral vibration of rope. So we use this kind of equation. Then seismic response analysis of wire ropes were conducted in order to confirm effectiveness of proposed method of analysis, and also the problem, to clarify the problem of earthquake disaster digital twin. We selected a lift system in this kind of 15-story residential building. This apartment building doesn't exist, but this is a typical apartment building in Japan. And we assumed the mass of each story and the stiffness is uniform, like this table. And the height of the building is about 44 meters. And the first natural period of the building is 0.88 seconds. And the damping ratio of 3%. And the next slide shows specification of lift. We consider two mass of car, 900 kilogram and 1,800 kilogram. 900 kilogram is empty case, empty load. There is no person in the car. And 1,800 kilograms is correspond to the full load. And the natural frequency of rope can obtain by using this kind of easy equation. And this graph shows relationship between rope length and the first natural period of ropes. And as you can see, for the car with 900 kilograms, if the rope length is about 20 meters, the natural period of the rope and the natural period of building will be equivalent. And also in the case of 1,800 kilograms, if rope has 29 meters in length, the natural period of building and ropes will be equivalent. So this case will be more severe case for the rope vibration. And we use 28 horizontal seismic wave actually observed in a particular part of capital area of Japan. We have strong earthquake observation network, so-called KNet, and we can select the seismic wave and we can download by free. So we can easily use 28 horizontal seismic wave. That having Japan Meteorological Agency seismic intensity of 3.0 or higher, observed since 2010. And this graph shows the response acceleration spectra. And you can see the seismic wave has predominant period about 0.2 seconds and also 0.6 or 7 or 8 seconds. So this kind of seismic wave was inputted into the building model like this. Then we pick the response displacement up and the input to the top and the bottom of lobe like this. And the next slide shows analytical result. This graph shows relationship between maximum ground acceleration and maximum displacement of wire lobe. And there are 28 plots in each case of lobe condition because we use 28 seismic wave. As you can see, in the case that mass of car is 900 kilograms, the green plot is larger. Green plot indicates the result of 20.2 meters in rope length. This is because vibration of the rope become larger when the natural period of the building is equal to the that of the rope. However, there are some variation in the response even if the rope condition is same. So I think this is because the characteristics of seismic wave. So accurate estimation of ground motion, seismic wave is more important. And this slide shows vibration mode of ropes. Because the first natural period of the building and the wire rope is equivalent, the first vibration mode appeared like this. And it is well known the first vibration mode is generally larger than the other higher mode. So finally, I'd like to make a brief summary of my presentation. So in this presentation, I propose earthquake disaster digital twin for apartment residential buildings with lift. And the vibration analysis method we proposed is suitable, effective for evaluating the behavior of rope. And the accurate estimation of the seismic wave is very important to predict the damage of the lift caused by an earthquake. Next slide shows future plan. In order to improve accuracy of our earthquake disaster digital twin, actual seismic experiment using a Seika table of an actual lift system in an actual building is required, I think. That's all. Thank you very much.
Thank you.
Thank you.
Does the construction of rope or the more non-traditional type of suspension systems change? Does the effect of the seismic waves, does it have a difference between the different types of construction of ropes? Is there something that's more optimum to use?
But what do you mean?
Depending on the construction of the rope, so what's the actual makeup of the rope, or some flat belt system or something like that, does the seismic waves have more or less effect on those type of equipment?
I think the effect for the building is more predominant, more main cause of the difference of the rope response, I think.
Thank you very much. This is a very interesting model. And just a question about your approach to model the rope. It is a linear model.
Yeah.
It is based on the string model. Have you ever considered that there might be earthquake which would act on the building in two directions? And then, just a suggestion, could you extend this model to take into account the coupling between horizontal and X and Y directions? That would require probably a bit of an upgrade. Just a comment.
Yeah, thank you very much.
Thank you.
As I shown you, this kind of damage will be induced by plane vibration. Yeah.
Thank you very much.
Thank you very much.